Hello, my name is Anna Zarasova, and today I would like to present our work in plasma chemistry data and plasma chemistry optimization and discuss how it can be potentially useful for ALD, ALE community and for plasma step modeling. So let me proceed to the next slide. So agenda of this presentation is divided in three main sections. First is an introduction where I will discuss where using modeling is appropriate or which kind of problems usually modeling is aimed to address. Then I will present a potential problem where modeling can be useful in case of plasma-enhanced ALD. In the second section, I will present examples of our work, how we use plasma chemistry optimization as a tool to improve modeling. And in the last section, I will do a little tutorial showing people who want to begin doing modeling how they can use free tools available on QuantumDB to start their plasma chemistry modeling. So let's proceed. So what problem simulations can help with? Essentially, the most obvious ones are testing hardware, new hardware design, also optimizing a new recipe, because the simulation will give you a better understanding of what's happening inside the chamber, and that will facilitate maybe identifying sources of some defects or new chemistry. A new precursor is arguably also can be enhanced by using plasma modeling. And of course, these activities are important for the bottom line of the companies because they ensure a faster time to market, reduction of costs, R&D, mitigate risks in research and development, and inspire innovation by giving researchers a much better insight into what is happening. Last but not the least is also it's a more ecologically friendly approach. Here is an example of potential application in case of plasma-enhanced ALD. So I used this, and the next slide is based on overview by Kremers and others, which I cite here. What they suggest is that as much as plasma-enhanced ALD has a lot of advantages, it also offers a limited conformality in case of high aspect ratio features. And the reason why it's happening is that because radicals which plasmas create, when they go down the deep trench, they are likely to recombine with the sidewalls, and the deeper the trench is, the less likely the radicals will reach the bottom of the trench. And this problem can be expressed as recombination probability. The recombination probability depends not only on the type of radical and the type of material with which it's colliding, but it is also very much connected with gas pressure, with plasma configuration, with deposition temperature, so various factors. Nonetheless, there is a correlation that the higher radical densities will lead to higher radicals penetrating deeper in the trench and enhancing the conformality. This sounds like creating this high radical density is something which simulations can be very helpful with. So naturally, ALD-ALE community is employing modeling, and the modeling is often required on multiple scales. So in this presentation, I will talk about reactor scale modeling. In this situation, we are talking about more macroscopic parameters and how your pressure, power, how these parameters can make a difference to the process. So if we want modeling to be helpful, we want it to be predictive. So we need a model which will predict the experiment. And to do that, there are different factors, and among them, for example, it needs to include the description of phenomena taking place, such as solving appropriate equations. But it also needs to include the chemistry data for the chemical processes taking place in the plasma. And also important factor for especially industrial users to benefit is that the simulation should run on a time scale which will be comparable to the one how long it takes to run experiments. I will focus on the two latter points because they are actually connected. So including all possible chemistry would be ideal. However, in many cases, it will hinder or make it completely impossible to run simulations with all possible species and all possible reactions. So naturally, people try to remove some reactions or species which seem to be less important, like, for example, removing them based on the small concentration and so on. On the other hand, run a risk then of removing some key species, which will make then your simulation results completely invalid. There has to be some way and a balance how to do it. So in Quantemol, we developed our own approach, and we tested it how to reduce chemistry sets without losing the meaning or without changing the results which the user wants to achieve with the simulation. So I will discuss these examples in the next section. Quantemol is using skeletal reduction approach to our chemistry optimization. And we have developed a software which is performing this optimization. So initially it starts with a 0D model run of the chemistry with all species. And in case of 0D models, they run usually very fast, even with hundreds of species and reactions. So after this first run, the algorithm ranks species, and then it proceeds to iteratively removing lowest ranked species and then comparing the results with the initial model output in order to ensure that the results with and without species are very close to each other. Then if the error induced by removal of the species is too high, then they are back re-added to the model. The advantage of this scheme is also that it ensures self-consistency, and it could be very efficient, which I'm going to show you in the next example. The first example I would like to present is N2H2 chemistry reduction. So the reaction set is based on N2H2 plasma chemistry taken from the paper by Hong, and it includes 42 species. So you can see them listed below. First of all, I would like to highlight here that the reduction is always based around certain conditions. So it's process conditions such as fixed pressure, gas temperature, power, etc. And also it is usually centered around some species of interest. And in this case, these are NH, NH2, and NH3. We have used our iterative reduction method and reduced the number of species from 42 to just 19. And 23 species were considered to be redundant, and I list them below. Also, if we compare the results of the global model for the reduced set and the detailed set, which you can see here, the detailed reaction set is a solid line and the dashed line is a reduced set, so they almost overlap for our species of interest. In conclusion, we have demonstrated that it's possible to reduce the number of species by over 50%, and also the simulation results didn't change dramatically for our particular conditions and for particular species of interest we had. So if you take, for example, this sort of chemistry now to the 2D modeling, as minimum you will get much faster calculations and better convergence. In the second example, we will look at the case where important species are formed on surfaces. So it is known that when the atomic layer deposition is done using N2H2 plasma, and in case of cobalt, the quality of film correlates with ammonia and ammonia-like N2H2 species. The more their concentration, the better will be the quality of the film. So naturally, we would like to increase the concentration of these species in the plasma. However, it is also known that these radicals are formed almost exclusively with plasma surface interactions. And unfortunately, for plasma surface interactions, they're not very well known and can vary from case by case. However, what we can do using our analysis, as minimum, we can identify which surface reactions will be key contributors to concentration of this important species. In order to do that, we have employed sensitivity analysis method developed by Morris, and the paper is linked in here. And what it does essentially, so we took all possible channels described in the home paper I referenced before of interaction between plasma and surface and species returning into plasma, and we perturbed them in kind of Monte Carlo fashion within a random sampling range I outlined here. Whilst initially these coefficients were all given arbitrary value and then they were varied, and then we run it with our 0G model and looked which variation had the most impact on our key species and on electron temperature. It turned out that there were actually three main reactions which were affecting the system and affecting our species and electron temperature the most. So this is when H arrives to the surface and returns as ammonia, or H2 also returns as ammonia, or H atom arriving on the surface and returning in H2. So you can see the charts comparing different reactions below. Because now we have identified the key reactions contributing to higher concentrations of this important species for the quality of our thin film, we can first of all prioritize these reactions to be calculated using different methods like molecular dynamics and reducing the uncertainty in our modeling. But also maybe there's some innovation could be developed in introducing the type of surfaces in the chamber, which will also give higher rates for these reactions, which will therefore facilitate higher concentration of the species we want in our plasma. In the third example, we are demonstrating how having most accurate information for your key species for some key reactions is fundamental for your simulation accuracy. In highly reactive mixtures like SF6O2, often species can be formed which do not have cross-sections data, or it's not very well known, such as oxygen-containing species. Calculating cross-sections for all of them is really time-consuming. It can take many weeks, but it may not be necessary. The reactions we identified as missing are dissociation and ionization of SOFX species, and we are making fairly commonly made assumption that these, in the first iteration, that these reactions will be the same as their equivalent for SFX species, such as that we assume that there won't be a huge difference if in SFX molecules one of the fluorine atoms is replaced by oxygen. Then we run our ranking algorithm for this system at certain conditions. So we fix pressure and power and gas flows. And what it seems to be giving us that actually SOF4 and SOF3 are quite key species for our system, and we do not have very precise information about them. So the next logical step is let's get the most precise information, at least for SOF4. To get a more accurate information on ionization and dissociation cross-section for SOF4, we have used our software called Quantemol EC or QuEC. This software is based on UK RMOL Plus codes, and these codes actually utilize our matrix method for calculation and quantum chemistry software MOL Pro. So this is an ab initio calculations, and so the main input parameter is just molecular geometry. We have also identified that dissociation pathway of SOF4 is more likely to lead to SOF2 plus 2F because SOF2 is a more stable molecule than SOF3. If you look at the graphs, where orange line is the calculated cross-section and the blue line is estimated, you can see that there is quite significant difference and probably it will impact our calculation results. This slide shows the differences we can see after running a global model with the cross-sections which we estimated and also with cross-sections which we calculated. The first one is electron density, and as you can see that it was seriously underestimated in case of the set where we just guessed our cross-sections, and for fluorine density it was also underestimated. We have also rerun our ranking algorithm, and it turns out that with the new cross-sections for SOF4, which were calculated and more precise, the importance of SOF3 molecule is significantly decreased, so it's no longer in our top 5 most important species. I hope this example has convinced you that knowing what species are critical for your system and obtaining most accurate information possible for them is actually fundamental for your simulation result validity. This is the end of the second part of the presentation, and in the third, the last part, I will give you a tutorial showing how to use Quantumol DB database. First of all, I want to make a bit of an introduction to Quantumol DB project. It was launched in 2016 and based on our customers' demand. People wanted to work with plasma modeling, but they also wanted to have a centralized place where they can find all kinds of reactions with heavy particles and electron scattering and various data which is needed as an input for plasma modeling. So we have assembled now a database which has over 18,000 data sets, in other words, rates or cross-sections. There are various particles, so it can be heavy particle collision reactions or electron scattering. It has full bibliographic references, so if you are working on publication, please do use them. And we also pre-assembled about 40 sets of chemistries that people can start with right away. So some of these sets also have a surface chemistry data. Let's then go to the website and see how it actually works. When you go to the website quantumoldb.com, it will bring you to this page. You need to sign up for a free account. Click on this button. It will bring you to a form, and then you will receive an email confirmation, and from then on you will be able to log in. What you can do on this website is you can search for the data or for reactions, and you can also look into chemistries we pre-assembled. But today, in this tutorial, I would like to show you how to assemble your own chemistry. So let's go to dynamic chemistry section. Yeah, so it brings us to this form, which will guide us through several steps in assembling our own set. I would like to assemble argon and oxygen chemistry, so I select my feed gases here and I click on button update. After the update, it brings me up the species which I can select, and the species are separated in the types of species, so you make your choices mindfully. So I will make my choices rather quickly. After selecting my feedstock gases, it brings me up all associated species which it could find in a database. So now I need to make my choices of what I would like to include in my chemistry. Go here. I will be building up a discharge for low pressure plasma, so I don't expect ozone to be formed. Then I click on update again. Now it selected all the reactions related to the species I included. Again, I will be making my choices now. And our recommendation is actually trying to start with relatively simple set. So don't select everything, but select the minimum and then add on complexity by adding other reactions. And now I can click on update. That's an important step. So now what we can do is we have three options, or we can download it. If you have gold membership, you can download it in any convenient format, such as, and we work together with different companies, like, for example, people who use CFDAs or COMSOL or VisGlo, so we can downloaded. And additionally, you can save a chemistry set and then retrieve it for modeling in the tools available online. Specifically, I will go to Boltzmann solver now. So we can, for example, add some other PCs. So let's add them here. Then we should. Okay, now let's calculate the rate. Okay, now we can see the results of this run. So let's look at the electron temperature. The thing to watch out for that it should increase monotonically and will be like a smooth function of the reduced electric field. So you don't expect any zigzags here. And to ensure validity, also look at the EDFs. So this interesting structure is related to resonances in the vibrational state of oxygen, but in general, these are smooth graphs, and that's what you should expect. If you have some kind of gaps or seeing low energy electrons, sudden peaks, some discontinuity, that suggests that maybe something is wrong. And if you cannot identify what it is, please contact us. Yeah, and here is our rate. Also, all of these graphs, they have logarithmic axis if you wanted to. Okay, so now we can use the same set, so you don't need to make any changes, then just go to this section called global model. And here, okay, so you can see that there are some macroscopic parameters you can change. Let's say I want to change, for example, make it different ratio for argon oxygen, and I can also set some specific sticking coefficients. So let's go here, and I can add I can also add pulsing to this model. So for example, I can make 4 pulses and make it 1 kilohertz and hit run. So let's look at results now. So here we have the actual values for densities. Here they are represented as chart, so you can visually compare them. Here our very nice temporal evolution of electron density responding to pulsing. We can also zoom in on graphs. We'll look at them with higher resolution. Here you see the button, and the same button we had on the Boltzmann solver, where you can restore a set if you wanted to work with it again. In order to evaluate more or less quickly if your model results are reasonable, so you need to ensure that, first of all, electron density shouldn't be 0, or electron temperature should not be higher than 5 eV, because usually these are two symptoms of the fact that discharge cannot be sustained with the given parameter combination. This is an online application. We also have an offline application which will do a little bit more of checking the data to ensure that you have a right chemistry set, such as will tell you if you have missing ion-ion recombination reactions or some terminal species. But try to work with this one, and if you have any questions, also feel free to email us. And now let's go back to the presentation slides. Most frequently asked question to Quantemol is actually what to do if you can't find the chemistry data you need. And of course, there are options like estimating it, which is the fastest way, or in some cases ignoring, although I hope I showed you that in some critical cases, you shouldn't ignore the data and it can affect your simulation's validity. In case of electron scattering, there are also trustworthy methods like R-matrix to calculate cross-sections. And in case of heavy particle collisions, there may be cases where molecular dynamic simulation will work. Feel free to ask us. We have tools to calculate electron scattering data, and we are working actually on the tools, including machine learning, to estimate data for heavy particle collisions. So stay tuned. To summarize, we have looked at the potential applications for plasma modeling and plasma chemistry optimization in particular. I also highlighted how important it is to have a small chemistry set, but which includes all the key reactions for your process conditions. And I showed you a tutorial on how to start today, tomorrow, working with Quantemol DB and assembling your own chemistry using free tools available there. I would like to thank my team, who you can be seen here, pre-COVID, non-socially distant times celebrating Christmas, and especially people whose work I have presented today. So it's Martin Henichinek, who developed our global model and also chemistry reduction algorithm, Sebastian Moore, who ran SF602 simulations for me, and Marie Tudorovskaya, who calculated SOF for cross-sections for me. Thank you very much for listening to this talk. Really happy to have had a chance to present our work here. If you have any questions, feel free to email us on support@quantemol.com. Also follow us on our social channels like Twitter or LinkedIn. And in the last slide of this presentation, I have actually put all the references to the sources I have used here. So the slides will be uploaded to Quantemol website, but also I believe they are accessible through GEC website. So go ahead, download them, and let's keep in touch and see each other next time live. Bye.